In parts 1 through 4 of this series, Classical Chemical Analysis for Small-Scale Miners, Prospectors, and Hobbyists, I discussed the topic of qualitative analysis. This topic focused on the determination of what elements or metals of interest that may reside in your samples. It did not touch on the concentration, that is, the amount of element or elements within your sample, such as grams per ton or percent per ton, etc. Before going forward and discussing the topic of quantitative analysis, which is the determination of concentration, there are a few items that requires discussion beforehand. So in part 5, the discussion will be limited to basic atomic theory. It will be focused on the formation of atoms and the process of combining to form different compounds. I will try to discuss this in a way that will be understandable to anyone that does not have a chemistry background. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. The atom, most of the time, is considered to be the smallest particle of an element. In the center of the atom is a positively charged entity referred to as the nucleus. Inside the nucleus, there are protons and neutrons. Protons are positively charged, and neutrons, which have a neutral charge, are made of smaller particles known as quarks. The discussion of quarks is beyond the scope of this presentation and will be omitted. As stated, protons are positively charged. The electrons that circle the atom are negatively charged, and neutrons basically add weight to the atom. It is the neutrons and protons that are of interest. The electrons that fly around the nucleus do so in what is called a cloud. The electrons that exist in the cloud do so in pairs and are arranged in orbits, which circle the protons and neutrons that encompass the nucleus. This is a representation of an atom. In the center is the nucleus, which contains all those positive protons. The electrons that orbit the nucleus are arranged in layers, referred to as shells, subshells, and orbitals. The shells are listed from 1 to 7, designated as K, L, M, N, O, P, and Q. These shells also coincide with the periods in the periodic table. More on this later. The main shells 1 through 7, or K, L, M, N, O, P, and Q, are further subdivided into subshells. These are the S, the P, the D, and F subshells. They also correspond to the periodic table as shown. The subshells are further divided into orbitals. Each orbital in the cloud can only contain 2 electrons. The S subshell has 1 orbital and therefore can only contain a maximum of 2 electrons. The P subshell contains 3 orbitals, hence up to 6 electrons. The D subshell contains 5 orbitals, which equals to 10 electrons, and the F subshell has 7 orbitals, and up to 14 electrons in the cloud. The periodic table lists the atomic number for each element that is known to exist. It starts with hydrogen and ends up with unenoctium. The atomic number also tells us the number of protons in the nucleus as well as the number of electrons circling the atom's electron cloud. Hydrogen has 1 proton and therefore has 1 electron. Helium has 2 protons and 2 electrons, and so on. The 1s subshell therefore will only contain either hydrogen or helium. The L shell, as shown, contains both the S subshell as well as the P subshell. Consequently, combining the 2 groups will contain not only the hydrogen and helium, it also has lithium and others right through to neon. As one goes down the table from left to right through each group, there obviously is a pattern. There is an order in which these shells and subshell orbitals fill. The electrons fill the subshells from the outside of the cloud, and by potential of the opposite charges between the protons and the electrons, the orbitals will fill from the outside inwards. The method of filling the subshells and shells is shown, but is actually reversed, as will be explained shortly. The periodic table shows 7 main shells, and the colored blocks represent the subshells. As shown, the electrons will fill the last subshells and the last orbital first, then proceed towards the center of the cloud to the first subshell, located in the first main shell, the K shell. The 8th group, being n equals 8, hypothetical as it represents the elements that have not yet been discovered or created. The last orbital, that is the furthest orbital away from the nucleus, are the electrons of interest. These electrons have been given the term valence electrons. The last shell of an atom is thus referred to as the valence shell. These are the electrons that react with other electrons of other elemental atoms to combine and form molecules. It is known that electrons are negatively charged and thus attracted to the protonic nucleus, which is positively charged. It is said that the electrons also spin, that is, rotate along an axis similar to our Earth's rotation, but the speed is much faster. When an electron is pulled into an orbit with another electron, there is a repulsive force that develops between them as both have negative charges. This, in a way, develops a type of friction between the electrons, which is the easiest way to describe it, which causes one of the electrons to reverse its spin. It is said that this neutralizes the repulsive force between the electrons, and they remain in their orbit around the nucleus solely by the attraction towards the positive nucleus. As an illustration, using the p subshell of the second main shell being n equals 2, or the L shell by name, there will be 3 orbitals. As the orbit fills, there will only be 1 electron in the first orbital. The second orbital will fill and only contain 1 electron. The same will happen with the last orbital in that subshell. As the 4th electron moves inward, it will replace a 3rd electron, which in turn will drop to the second orbital. As this happens, it will replace the 2nd electron and it will move into orbit with the 1st. This will continue in this manner until the entire p subshell is filled. As soon as the number of electrons in the orbitals match the number of protons in the nucleus, the atom is said to be complete chemically, but not electrically. The periodic table shows 18, that is group 18, as the noble gases. When an atom has the same number of electrons as there are protons and the valence shell is completely filled, the atom is said to be inert or noble. This means that the atom is completely both chemically and electrically. Inert atoms resist change. They do not combine easily with any other atom, either ionically or covalently. As the ionic charge of the atom is given, and on the right-hand corner of each elemental block, the noble gases have their charges listed as 0. They are neither positive nor are they negative. Therefore, they do not combine with other elements. There are 2 ways that atoms bond. The first is ionic bonding and the second is covalent bonding. Let's focus on ionic bonding first. As shown, the periodic table lists the ion charges of each element in the table. As mentioned, the noble gases have the charge of 0 shown. It is also important to note that carbon has no charge listed. The metals that are shown in the previous slide, colored green and red, those blocks of elements are referred to as representative elements. Counting each element in each of the green and red groups from left to right signifies the number of valence electrons in each valence shell. Counting the elements in the L shell starting with lithium, when you arrive at carbon, the number of valence electrons will equal 4. Oddly, 4 is not listed for this element. However, this element can either take on an electron or give up an electron. More on redox reactions in a future presentation. But for now, any atom that has valence electrons, fewer than 4, will want to give away its electrons, and those that have more than 4 valence electrons will want to take electrons. Sodium has only 1 valence electron. Chlorine, for this example, has 7 valence electrons. As a sodium atom in solution comes closer to a chlorine atom, it will expel an electron. The chlorine atom will grab that electron to complete or completely fill its valence shell. Sodium losing its electron becomes more positive. Chlorine gaining the electron becomes more negative. The electrostatic forces becoming stronger brings these two atoms together like magnets, forming a molecule of sodium chloride, commonly referred to as table salt. Each atom that may have been in the solution is called an ion, hence the term ionic bonding. The second process is covalent bonding, that is, a sharing of electron orbitals. Oxygen has 8 protons and 8 electrons. The L shell, or shell number 2, has 2 subshells, S and P. The S subshell is complete with 2 electrons. However, the P subshell, having only 4 electrons, is not complete. The P subshell of incomplete orbitals wants 6 electrons for a complete valence shell of 8 electrons. The sulfur atom has 16 protons and 16 electrons. The M shell has 2 subshells, S and P. As with oxygen, its P subshell has only 4 valence electrons. It too wants 6 for a complete valence shell of 8 electrons. If both of these atoms, hence ions, were in solution, as they become close to each other, their outer electrons would combine with each other at the outer orbitals. That is, they will share their orbitals with each other. As depicted, the 2 electrons from each atom will share each other's orbitals, giving each atom the required full valence shell of 8 electrons. Counting the electrons within each of the valence orbitals for each atom will give you the required 8 electrons for each atom. This results in a very stable covalent bond. As shown, there are 2 electrons from each atom sharing orbitals, resulting in the bonding of the 2 oxygen atoms with 1 sulfur atom. Since there are 2 electrons in each atom bonding, it is referred to as a double bond between each of the atoms. This is easily represented in a Lewis dot diagram. Each dot represents an unbound electron, and the solid lines represents the electron bond. The 2 solid lines between each atom represents the double bonds between them. The diagram also shows the molecule as a polar molecule. Dipoles are not discussed as it's beyond the scope of this presentation. Basically, there are 4 main reactions that can take place: synthetic, single displacement, double displacement, and decomposition. The periodic table shows the ionic charge of the elements, which is different from a formal charge. I will show both in the examples. However, a formal charge is shown as the plus or minus symbol in front of the numeric, and the ionic charge symbol is behind the numeric. The formal charge of a stable atom or molecule is always 0. For a synthetic reaction as shown, a copper-2 atom combining with 2 chlorine atoms results in copper dichloride. The equation shown is a balanced equation, and the formal charge of the molecule is also shown. For a single displacement reaction in solution, the sodium chloride will decompose into sodium and chlorine ions, or atoms. The copper-2 atom will combine with the chlorine atoms, resulting in a copper dichloride molecule. Note that the sodium has an ion charge listed. However, the formal charge would be 0. Dissolving copper dichloride and silver nitrate into solution, these elements will decompose into separate elemental ions, that is atoms, then recombine into silver chloride and copper-2 nitrate. Note the decomposition can occur if enough heat is applied as depicted with the water molecule, resulting in the release of both gases, or it can be brought about by dissolving the material in a solution. Polyatomic ions, as already discussed, also have ionic charges. Now, due to their strong covalent bonds, they do not dissociate easily. Therefore, they have the characteristic of being a single atom. If there is only one polyatomic ion in the formula, brackets will not be shown. If there are more than one polyatomic ions in the formula, brackets will be shown as given for copper 2 nitrate. There is a pattern to which these elements will recombine. This is shown by the arrows. This is not only accomplished by their ionic attraction between their negative and positive charges, but also due to their electronegative values as well, and is beyond the scope of this presentation. But it is enough to say, in general, one can predict the results of a reaction as shown. At this point in time, I need to talk about a mole, and no, it's not that cute little ground-dwelling creature. It's a concept. I covered this concept in my fire assay series, however, it needs to be discussed here. It's a very important concept, and it is used consistently within the realm of chemistry. A mole, which has the symbol MOL or small n, can be anything. It is used to calculate the weight of a molecule or material, as well as concentration and other procedures which will be presented in the next part of this series, part 6. We can, for example, say that 1 mole year equals 365 days, or 365 days equals 1 mole year. We can extend that by saying that 1 mole day equals 24 hours, or 24 hours equals 1 mole day. It may also be said that 1 mole of silicon equals 27.0 grams, rounded off, or 27.0 grams equals 1 mole of silicon. Now, through the process of elimination, an unknown can be calculated quite quickly. For example, if we wanted to find out how many seconds there was in 1 calendar year, well, 1 year is what we can well work with. Since we have 1 year, we know that 1 mole year has 365 days. We also know that there is 24 hours in 1 mole day, there is 60 minutes in 1 mole hour, and 60 seconds in 1 mole minute. Well, through the process of cancellation, the year, the days, the minutes can be cancelled out. This has left us with the remaining being seconds. Multiplying the numbers divided by the denominator gives us a total of 31,536,000 seconds per year. This concludes part 5 of this series, Classical Assay for Small-Scale Miners, Prospectors, and Hobbyists. I tried to introduce you to some very basic atomic theory. I purposely left out a lot of information, and in doing so tried to provide the information in a way that any individual without a chemistry background would be able to understand some of the principles without overwhelming you with what was being imparted. I tried to explain how atoms bond to form different molecules and thus hope that it was presented in a way that was understandable without a lot of theory. With this information, hopefully, you will be able to predict the product or what product will result from a chemical reaction between reagents. And last, I tried to introduce you to what is referred to as a mole. That is the mole concept. The mole concept will be used consistently throughout the upcoming presentations. In part 6 of the series, I will be discussing solutions. This topic will be separated into a couple of presentations going forward, and it is an integral part of quantitative analysis. For anyone that finds the topic of mineral assay interesting, I encourage you to take Chemistry 11 and 12. These are free courses in the province of British Columbia through eBus, which is run by the Ministry of Education. There are other programs as well, which are provided by the different school districts. eBus is administered through School District 57. College chemistry courses 114 and 115 are also recommended. As for a mineral assay course or program, I highly recommend the British Columbia Institute of Technology, which is located in Burnaby, BC. They offer a distance education program as well as an in-house program. I hope that you will view the next presentation when it is published. If you find the topic interesting, or if you know someone that would benefit from this series, give it a like and a share. It's my only reward. I'm Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.